Well, hello, Bearcats. It is time for our first calculus video lesson of the year, which means I am trying to make our first calculus video lesson of the year. So, just a couple things about our video lessons. I'll just go through the main points of what you're going to need to be successful with the questions that are in the chapter and the portion of the calculus text that we're covering. And your job is to take notes. You write down some key ideas. You write down some key statements. At some points during the video, it will pause, and you'll be expected to answer a question, and then it will continue on. So with that said, make sure you're paying attention and listening up, and we will be getting together and going over everything in class afterwards. So get this done before class starts so you are ready to digest this and to process this and to discuss this. Today's lesson is pretty straightforward. It's straight, just straight, what is it? Like, why are we doing this? What is up with this whole calculus thing? Why do I need it? Why do I need to torment my life for a year in high school? Well, the truth is that calculus is created so that we can better understand lots of important things that we deal with. It is a far more intricate form of calculating. So, for example, up to pre-calculus, we've learned to do a bunch of things. Here's a list. So, for example, in pre-calculus or Algebra 2 or Algebra 1, we learned this pretty straightforward fact, and it was really important to us. It was called the slope of a line. And it basically said that if we got any 2 points, that we could find the slope of a line by subtracting the y values, y2 minus y1, over x2 minus x1. So any 2 points, we could draw a line between them and find the slope. In calculus, we're going to be finding the slope of a point. So think about that concept. Our slope formula requires 2 points, but in calculus, we're going to actually find the slope of something called the tangent line, and the tangent line only has 1 value. So that makes it complicated. So for example, it'll look like this. Like here's a secant line, right? A secant line through a curve. I can say, hey, what's the average slope? What's the slope of this line if I start at this point and I go to this point? y2 minus y1 over x2 minus x1. And then suddenly in calculus, I'm like, okay, I need the point right here where it doesn't go through this thing at 2 points. It only connects at one spot because that's actually something that's a little more valuable for me. Okay, this is going to be an average value, which happens over time. And this is going to be something called an instantaneous value that happens at the moment. For example, here we go. Let's think about this in terms of what we learned in middle school. Okay? Middle school, we learned about distance, rate, and time. We learned distance equals rate times time. Remember that? So all we had to do was know if we wanted to find the rate of something, that we would just have to know how far something traveled and divide it by how long it took. So if I knew 2 points in a travel, if I figured I went a certain number of miles in a certain number of hours, I would get miles per hour. It's super easy to calculate. Well, what if I asked you to calculate the exact speed at 1 point? So think about that. In calculus, if I am going to find this instantaneous point, this instantaneous rate of change, this instantaneous speed, then I'm only going to have one point because I'm not going to tell you can't tell me the distance I traveled and how much time it took if it's only 1 point. Because if it's only 1 point, you didn't travel anywhere and it didn't take you any time. But you know you are traveling a speed. So that's what calculus is going to allow us to calculate. Also, second half of calculus for AB is going to talk about this idea of area, this idea of calculating the area of objects. And you're like, dude, I pay attention to geometry. I fully understand it. Rectangles, bro. Rectangles. I know. The area of a rectangle equals base times height. We all know that. We all know the area of a rectangle, right? We know the area of a triangle, half a rectangle. We know the area of a trapezoid, 1/2 base times the sum of two heights. And no, 1/2 height times the sum of two bases. Right? It's the average of the two bases multiplied by autologous. Basically, you just turn it into a rectangle. That's what geometry was. Geometry was taking any shape you gave me and turning it into a rectangle. That was it. Well, in calculus, what if I give you a shape like this and I say, hey, find the area of that thing? Because the problem is that if I want to find the area of that thing, it is not rectangular, and I can't just cut and paste, and there's no pretty formula, and this curve is always going to be some different curve. And actually, you know what we're going to do in calculus? It's so funny. It's like so anticlimactic. We're literally going to turn it into a bunch of little rectangles, and then we're going to find the area of all those little rectangles and add them together. That's literally what we're going to do mathematically in calculus. And if we can do area, what else can we do? Clearly, we can also do what? Volume. That's right. Because volume equals length times width times height for a basic rectangular prism. However, what if I gave you something super funky like that? This, by the way, this isn't even a circle. This is actually a three-dimensional object where this function is y equals negative x squared. Yeah. And then I got to find the area of this and then figure out the volume of this. And okay. Yeah, that's calculus. That's what we do. So that's basically the idea of why we need this. I have a question for you on the bottom. It says, why do we need calculus? So I would like you guys to think about that. And I'd like you to come up with an answer for that and submit it. Hopefully, you thought about it. You thought about why you need calculus. There's lots of reasons for it. Hopefully your answer has something to do with this. We need what? Let's try that again. First video. We need to be able to calculate. Let's go with instantaneous speed, slopes of tangent lines, and areas and volumes of irregular, how's that one? Irregular shapes. Okay. Whoa. Hold on. I got a speaker that is in the way of my, okay, go. Right? So this is an example of why we need calculus. I'm sure that you came up with way better ideas, but you know, is what it is. Okay. Let's talk about the second page. Things are going to get a little bit funky. So here are the main topics of calculus AB. There's three basic things we do. One, this chapter, we do these things called limits. Two, next chapters, we do this thing called derivatives. Three, third chapter, we do these, or fourth chapter, yeah, we do these things called integrals. That's it. There's like three topics for the whole year. They are kind of complicated, let's be honest, but that's it. So here's an example of the tangent line problem. This is a classic calculus question. It's the main focus of chapter 2. And it's all about derivatives. It's about this idea that if I can calculate the slope of any secant line, right? This is called a secant line. If you remember from geometry, a secant connects a curve in 2 points. And if I connect it, then it's allowed, then it crosses it, so I can find the slope of it because it's got 2 points, right? Because the slope of this, if I go from P to Q, the slope of this is going to be y2 minus y1 over x2 minus x1. I should be able to calculate that, right? So when we study tangent lines, remember, tangent lines don't do this. They don't connect in 2 points. They only connect in one. A tangent line, like this one right here, only has one value in it. It's only got that p-value. That's it. That's the only place it connects with this curve. So for us to find the slope of this tangent line, we can't just connect two dots. So what we actually do is we do this. This is the cool part. We say, hey, what if it was a secant line? Like, what if the second point was way up here? And I calculated the slope, and I did the cool math and everything. And what if I got a slope of 1? And then I was like, you know what? I'm going to move this point closer to P. I'm going to move this point here. I'm going to scooch it in a little bit. So now the Q value's here, and look at what happened to the slope. It went down, right? And maybe I calculated this. I did the cool little thing on the calculator, and I got the answer. And maybe for this one, I got 0.6. Slope just went down, right? And then I scooted it in a little more. Maybe I scooted it into here. Q is now even closer to P. It's actually getting closer and closer and closer as I go down the curve. And now maybe the slope, which is a little more, turns out to be like 0.4. I am making these numbers up. The actual number is not significant. And then I go a little closer. Maybe I go here. Maybe I put Q that's pretty close. That's pretty close to Q. And now maybe that slope is going to be 0.3. And maybe I keep doing that. Maybe I choose, you know what, 0.3 is actually, look, isn't this line closer representation than this line? Than this line? Like, this line is super close to this tangent line if I'm thinking about the slope of it. And what would happen to my prediction if I took Q and I moved it even closer to P? Wouldn't that mean that my new line, if I put it like right here, wouldn't my new line actually be even closer? Maybe I got M of 0.2, right? So every time I move Q closer and closer to P, my slope gets closer and closer to the slope of the tangent line, right? And that's what we're going to do. We're going to do that mathematically. We're going to say, let's move this point closer and closer and closer. Get this. Until that point is infinitely close to P. Infinitely. And then we'll calculate the tangent. So the distance between the 2 points will be 0 in height and 0 in the x direction. Calculus. And we'll calculate an actual answer. We'll get like 0.37 or 0.45. We'll actually get an answer for it. Scary, huh? All right, I'd like you to finish this statement. It says, if we are calculating the slope of a secant line, like this one and this one and this one and this one and this one, as we move Q closer and closer to P, what happens? What does it tell us? Answer it. All right. Hopefully, you wrote something like this. As we move this Q value closer and closer to P, the slope of the secant line becomes closer, we're going to write in value, to the slope of the tangent line. Yep. Until it's infinitely close, and then it is going to be infinitely correct. Right? We will be able to find the exact slope of the tangent line, even though we're not exactly at the tangent line. It's crazy stuff. Because calculus. All right. Another thing for calculus. Here we go. Finding the area problem. So we have a finding the area problem right here. This is using integrals. So if I'm finding the area of something using integrals, I could do basically this. Like, imagine I had a curve, and I'm like, tell me the area under this curve. I need to know the area of everything from A to B. I need all of this area, and I need you to calculate it for me. So you would probably go through, and you would calculate, well, you'd be like, I can't quite get it all. But you know what I could do? I could split it up into 4 rectangles, and I could get what we call an estimate, right? I can just estimate it. I could say, you know what? I'm going to calculate the area of this rectangle. What's the height? What's the width? This rectangle. What's the height? What's the width? this one, what's the height, and this one, what's the height, and then I'd get my area. Now I would have a problem because clearly there's a space here and a space here that I did not count. So that's why it would be an estimate. It would be pretty inaccurate because I got these pink spaces that are a little bit more than the area that I guessed. I would have an underestimate. So what if I chose to make rectangles that were smaller? Like what if instead of 4 rectangles, I made 1, 2, 3, 4, 5, 6, 7, 8? What if I doubled it? What if I made 8 rectangles instead and I wedged them in here? And then I found the area. And then I made an estimate, right? First of all, what would happen to the width of these rectangles, right? The width would get smaller, but the area that I finally calculate, I mean, look, the pink space got really tiny. Like, look at the size of that pink space, and then look at the size of these 2 little pink spaces, right? So even though my rectangle, I made more of them, my estimate is going to be closer, right? More rectangles, closer estimate. Here we go. Calculus question. What would happen if instead of 4 rectangles or 8 rectangles, I decided from A to B, I was going to make 100 rectangles? No, sorry about that. 1,000 rectangles. No, wait. No. 1 billion rectangles. So I would calculate 1 billion rectangles. I mean, I would sit there and I would draw 1 billion rectangles, right? That means every single rectangle would be super thin, like crazy thin. But how accurate if I did like 1 million or 1 billion rectangles? That's 1 million. How accurate would that be? It would be very accurate. There would be almost no missing spaces at all. It would be super accurate. As a matter of fact, if I had an infinite amount of rectangles, it would be infinitely accurate. Once again, the raising of infinity. That's calculus. Calculus, we're going to make infinity rectangles for every problem. And we're going to add up an infinite amount of rectangles. And we are going to be infinitely correct. It's kind of cool. All right, I'd like you to finish the statement. It says, if we are estimating the area of a region under the curve, the more rectangles we draw, finish the statement. Hopefully, you wrote something like this. The more rectangles we draw, the more accurate our estimate. That's it. Calculus, man. Okay, hey, jumped ahead there. Little video editing. I started to go over some example problems and decided, you know what? That's going to be our live instruction piece in class. So, ladies and gentlemen, good luck with this. As a matter of fact, here's what we're going to do. We're going to start with number 5, and that's going to be the last question that you're going to have to answer for this video. So good luck on number 5, and we'll catch you in class, and we'll be going over all these together and probably doing a little homework. Laters.